welcome to the next meetup organized jointly by quantum computing groups with from Washington, D.C., Toronto, and Warsaw. My name is Pavel, and together with Dr. Sebastian Zając, we will be the moderators of the meeting today. And we have pleasure to host our great speaker, Dr. Edo Giusto, who is an assistant professor of the University of Naples in Italy. The title of the talk is Quantum Reliability, Circuit Susceptibility, Fault, and Integration Issues. Before we start, I would like to give you a few announcements. So first of all, as you can see, the meeting is recorded, so hopefully the video will be later available on our YouTube channel as usually. And we've also agreed with Edo that if there are some urgent questions related to the particular slides, you can raise your hand and we can try to interrupt and ask the question. If the question is not urgent, if there are some more general questions, let's keep them for the end. So you can write your questions on our chat, and after the lecture, there will be a Q&A session where we'll just try to ask all the questions. Okay, so we would also like to announce and invite you to attend our next meetup. So the next one will be in June, on June 8th. Dr. Siwan Yu will tell about practical quantum computing, toward practical quantum computing, addressing crosstalk and circuit optimization. Later in June, Dr. Emil Jacques will tell about simulation of quantum chemistry Hamiltonians with relativistic effects on fault-tolerant quantum computers. Later in June, Elliot Miller will tell about deep learning generalization. So this talk will be related to AI and not quantum computing, but maybe there will be some applications in quantum computing as well. Novel methods for ensuring AI can be trusted. And then in July, physics of light dense matter, quantum and classical effects. And the talk will be given by Dr. Shanti Dimiet. And later in July, Martin Mushal will give another talk about AI, this time about generative AI and beyond. And on July 27, Zeki Seskir will tell us about educating to the culture of quantum technologies, a survey study on concepts for public awareness. And finally, in August, I will give a talk about optimizing complex processes using AI and quantum computing. So finally, we would like to thank our partners and sponsors for supporting us and helping us organize this event. And that's all from my side. So I will now stop sharing my screen. And Edo, first of all, thank you for accepting our invitation to give this talk. And if you are ready, the Zoom is yours and you can start.
Thank you. Thank you, first and foremost, to Aaron and Pavel and for Sebastian for the organization and for inviting me. So in this presentation, we are looking at what are some of the issues in integrating quantum computers with classical supercomputers. And especially, we're going to analyze, what are the effects of faults in the quantum domain. So this is the outline of the presentation. I'm just going to give say a few words about myself and an intro on the topic. I will talk about noise in the quantum domain and QuFI, the quantum fault injector developed for this domain with some applications. And then I will conclude with some final remarks. So this is me. I did all my training in computer and system engineering at Politecnico di Torino, so northwest of Italy. Last year I was visiting postdoc at the Superconducting Quantum Materials and System Center at Fermi National Lab near Chicago, thanks to the Next Generation Enrichers Fellowship. I'm a technical committee member for IEEE QCE, so the Quantum Week conference, ICCE, which is a conference on consumer electronics, and I'm also a member of the Consumer Technology Society for Quantum in Consumer Technology, and I'm also guest editor for a special issue on frontiers in computer science titled Realizing Quantum Utility, Grand Challenges of Secure and Trustworthy Quantum Computing. And I'm also a Qiskit advocate. So enough about me. In here, so I think all the people that follow these meetups are interested in quantum computing, and we have several applications with proven speed up in domains of quantum simulation, discrete optimization, solving linear systems, and then we have a huge domain drive from high energy physics, from AI, from planning and routing. And these are all tasks that usually we carry out with classical supercomputers. So are we there yet in exploiting quantum computers for these applications? Not quite, because there is no, I mean, this is arguable. At the moment, still, I cannot see like a quantum technology which is mature enough to carry this out. And a related question is, will we ever have like a standalone quantum computers? I don't think so, personally. I believe that the quantum computers will be the next generation of coprocessors, like what we have now for like GPUs and TPUs. And this means that we need to integrate integrate quantum computer into high performance computing system. So this is the dawn of a new computing paradigm, HPC QC, because we are merging bit-based classical computers with qubit-based quantum computers. And just as a reference, just to give you like a scale of the complexity of classical supercomputers, this is these are the first four positions in the ranking as of 3 days ago. And we have, as we can see, we have frontiers in Oak Ridge National Lab, Aurora in Argonne National Lab, Eagle in Microsoft Research, and Fugaku in Japan. And as you can see, they are huge. There's no other like way to define them. They are just basically huge, and they consume a sheer amount of power, both like to for them to function, and also for cooling them down, because they are quite packed dense. And Frontier is the first exascale computer, and by exa I mean 10 to the 18 floating point operations per second. So as you can see, all of these are like very complex already. So how do we do this? How do we integrate these two kinds of paradigms? Like, are we going to have like a large arrays of QPUs, like standalone QPUs, or are we going to have QPUs with CPUs, sorry, with a quantum processing unit, QPU as accelerator? And also, how do we integrate the quantum computing inside classical workflows? Because in the end, for the supercomputer user, I mean, they just don't care about how the solution is provided. They're just interested in the solution. So how do we define the models for programming such a hybrid, such a diverse system, and how do we manage the resources and the performance for such heterogeneous systems? In here we have three possibilities to carry this out. We have on the left we have a cloud system which is connected to QPU, which is basically what IBM does. So you program, you write your program on your laptop, and then you hit send, and it arrives in the cloud system, and then the cloud system programs the QPU and executes the calculation and then sends you back the results. But this is not scientific computing. That's no way around it. In the example in the middle, we have several classical nodes. Each of them has associated QPU, and they are interconnected with a classical interconnection. But then how do we handle such resources? How do you decompose a certain problem? Because if the sub-problem is like too small, there is going to be no quantum advantage. And also, how much time does it take to decompose a certain problem? Maybe if you just simulate it on a GPU, it's going to take less time and be more efficient. The third option would be very similar, but also with a quantum interconnection. So between the QPUs, but then how do we handle this? Like, how do we coordinate the quantum signals in between the QPUs? And then there has to be some sort of classical system to handle this. So we have an overhead for such communication, and so it's like there will be some trade-off between exploiting the quantum capabilities and then getting like bogged down with control. How would the quantum node model be like? Well, we could have again like the classical part, of course, with the central processing unit, memory, GPU, and classical interconnection, and then this quantum processing unit, which has the inside the quantum control unit to decode instructions, the execution unit to send signals to the quantum register, so the qubits, and then this quantum network interconnection. In such a model, we could have the CPU issuing instructions, so we need to go in memory, fetching them, decoding them, for the letting the QCU parsing them, issuing the operand to the execution unit, which applies these fields, and then qubits evolve, and when we read back the qubits, we collect this data and we send these values back to the QPU. And like all of these tasks can be structured in this high level in a high-level architecture such as this one. This is an example by the XACC framework developed at Oak Ridge National Lab. And then in this architecture, you start from at a high level, you write your program in whatever language you like. You can use Qiskit, you can use OpenQASM, you can write D-Wave framework, and then this high-level language gets compiled to some intermediate representation, as it's done also for like classical computers. So when you compile some language, and so we have different levels of optimization and transformation of this intermediate representation, and then we iteratively process this depending on the backend that we want to execute our workload on. It can be IBM machine, Rigetti machine, or whatever else. And so in executing this and like setting up these systems, we need to take into account performance parameters, such as how large, what kind of area do we need to build this, what are the errors that we are going to see in such system, what are the latency for all the different components, what is the accuracy of the solution, how much time does it take to get the solution, and how much like total power this system requires. And in this, one of the the topics that interest me the most is resiliency. So, and resiliency can mean lots of stuff in this domain in particular, because it comprehends, like, it combines the compilation of code from your high-level language down to the pulses that you need to apply to the QPU, and also not only that process, but the way back, meaning we need to check, we need to verify that sequence of pulses actually implements what the quantum workload was thought for. Okay, and then how do we check the reliability, the complexity of the control of these devices, and how do we define models and methods to carry out this, fault tolerant hybrid architectures, and in particular in this, how do we deal with faults, both in the classical and in the quantum domain. One of the main sources of faults is cosmic rays, and cosmic rays are basically showers of particles coming from outer space and decaying into high energy neutrons that act on transistors, and also a lot of other particles that have an impact on superconducting qubits. And in this presentation, I'm going to focus on superconducting qubits, just because that's one of the most widespread technology. And in a classical CMOS transistor, this ionizing particle arriving on the substrate of the chip generate electron-hole pairs, releasing and depositing an charge. And if you have a charge that is sufficiently large, the transistor can flip its state. And this would turn into a masked fault if there is no effect on the output of your program, or if that particular memory cell, for instance, is not used, or silent data corruption if your program yields an incorrect results, but it keeps on going, and detected unrecoverable error if either your program crashes or the entire device has to be rebooted. What does happen in quantum devices, with a focus on superconducting qubits? It's much more complex because you have systematic noise due to errors in the control and readout, so driving and reading the state of the qubits, for which on one side we need to properly calibrate the devices and improve hardware, meaning improving the manufacturing process. So how do we build qubits, how do we build Josephson junction, etc. And then stochastic noise given by random fluctuations. A part of cosmic rays, we also have thermal noise because superconducting qubits are quite cold inside the dilution refrigerator, and the liquid helium moves, and you can have noise due to this, and then also we have magnetic fields and electric fields, which we cannot fully avoid. The quantum noise can be characterized, can be in several components. We have longitudinal relaxation if we go from the excited state to the ground state, or excitation the other way around. Pure dephasing if we move along the equator of the Bloch sphere, or more commonly a combination of the two. We have a transverse relaxation. And one of the most influential paper on the impact of radiation on superconducting qubits was carried out by Google Quantum AI in 2020, at the end of 2021, if I remember correctly. And they used their Google Sycamore computer, the one that they use for the quantum supremacy paper, which is a 10 millimeter by 10 millimeter chip on which 25 qubits were running, and they recorded faults of a duration of 25 milliseconds, which is much longer than a single execution. And then this happens every 10 seconds on average. And how did it did this? They prepared the excited state, letting the system idle for 1 microsecond and measuring. So since we have probabilistic measurement, they would either get 1 or 0. And in normal operating conditions, you have a baseline of around 4 errors out of 25 qubits. And then you have a particle strike, and then you see that basically all of the qubits collapse at the same time. And then you have a gradual return back to the baseline with this transient lasting for 25 milliseconds. And to put this in perspective for what happens, in traditional computers. Titan is now decommissioned supercomputer that was again at Oak Ridge. It had 18,000 nodes with a ton of RAM, and each node with 4 CPUs. Hours were necessary to observe a corruption due to radiation events. Let's say similarly, to some extent, to what happens in a transistor, but not quite. This is the scheme of Josephson junction, which is the core of the superconducting qubit. The charge, which is deposited by the radiation in a substrate, generates these electron hole pairs that induce non-equilibrium that breaks the Cooper pairs and produces quasi-particles, so electrons. And these quasi-particles can tunnel the junction, changing the state of the qubit. And we believe that the excess of this excitement can be logically translated to a shift in the qubit state with a magnitude that depends on the amount of charge deposited, and also that the closer you are from to the particle impact location, the higher this charge, and so the higher will be the shift. But I'm sure that people following this series will say, yes, but we have quantum error correction. It's going to deal with it. Usually, quantum error correction techniques deal with intrinsic noise, but is expensive, and usually you need like 100 times larger circuits, and does not work for events caused by cosmic rays, because these events are correlated, so they create correlated errors both in time and space. So if you are using more than one physical qubit to encode a logical qubit, but then like a chunk of these qubits are destroyed, the state is destroyed for this. Due to this, there is just no way that you can recover from this error, and these events are definitely not predictable whatsoever. So what are the possible countermeasures for such issues? We can bury it deep underground and shielding with lead, as Laura Cardani from INFN is doing here in Italy in Gran Sasso, so putting the machines under 4 kilometers of rock. Or we can use redundancy, as Rodney Van Meter and colleagues are suggesting. So having distributed hardware, so different QPUs connected with a quantum network, sharing entanglement between them. Yeah, these may be viable solution, but definitely they are not neither easy or cheap. We can think of improving the hardware, and Professor Martinez suggests to insert quasi-particle traps in the chip, and now it's something that everybody's doing. And also engineering the gap, so the amount of energy that's required to change from one state to from the ground state to the excited state in the chip, as suggested by again by the Google Quantum AI people. And so at this point, is the problem solved? Definitely in hardware. I'm not sure. But what can we do that is cheap and reasonable using software? And this is why my team and I developed the Quantum Fault Injector. Fault Injector, as it's common to do for classical digital circuits, in where you inject faults in a certain circuit and then you observe how these faults propagate throughout and how they influence the output. QuFI is able to identify circuit and qubit sensitivity to diverse sources of faults. So it's general, it's not like specific for cosmic rays. It's interoperable with Qiskit and Pennyline frameworks. Is flexible because you can perform multiple injections on neighboring qubits. You can work with simulators and with these machines, and it adds on top of the intrinsic noise model already available for a certain machine. It's based on a new metric that we introduced, the quantum vulnerability factor. And of course, it is open source. So in here is the link and the QR code. You can check this out. In this framework, the injected faults are modeled as additional parameterized gates that are added to the circuit under test. In this example, we have the burst in Vasirani circuit with an injection, and then the evaluation of the output correctness. Like a theta shift of pi over 4 is injected on the first qubit after the first Hadamard gate, and that particular injection modifies the output probability from the blue one to distribution, sorry, from the blue one to the red one. And to model this injected fault, we need to have different, phase shift of different magnitudes, and so we use the U-gate, which is the generic most flexible gate available in Qiskit. And we inject on the phi angle each from 0 to 2 pi each 15 degrees, and on theta from 0 to pi each 15 degrees. Just a few words on the quantum vulnerability factor, which is the probability for a fault to propagate and alter the output. It is similar to other metrics in the classical domain, architecture and program vulnerability factor, in the sense that it goes from 0 to 1, and the close to 1 is worse. As an example, for this, a certain circuit, it's not important what circuit it is, but in the fault number 1 case, the QVF is very low because that fault doesn't have a great impact, and the correct solution, which is 1-1, can be confidently selected. In the case of fault number 2, we have that the QVF is 0.5 because we have basically 50% probability of selecting the correct output and 50% probability of selecting the incorrect output. And in case of fault number 3, we have the QVF is 0.63. We have a higher chance, as you can see, to select an incorrect output. We decide to plot the QVF values as heat maps to help visualizing, like at the first glance, what's the effect on the selected circuits to identify, the most critical points that could be then the target for future hardening techniques. So the green color indicates a low QVF value, so the correct state can be confidently selected. Red color, an incorrect state is more likely to be selected, so QVF is higher. White, we're not sure. And actually, the gradient is set at 0.5, but you can tune it depending on the criticality of your application. Just visualizing what are the shifts that we are injecting. If we are injecting on theta, we are moving along this meridian. Instead, if we are injecting on phi, we are injecting along the equator. Let us take a look at some examples. So these are the heat maps for a single injection in some of the most famous circuits for quantum computing, Bessel-Masirani-Dojciosa, and the quantum Fourier transform algorithm. We can see that Bessel-Masirani and Dojciosa are affected in a similar way, while for the QFT circuit, the response is somewhat different. We can see that for this particular set of angles, we have a more tolerable effect when both angles tend to pi, and we do not see this for QFT. We can analyze, so the framework is flexible. You can analyze the qubits one by one, because maybe you want to, but some of them may be more critical than others in the computation, and we could want to protect them differently, and also because like physical qubits could be more or less reliable because they have different noise profiles, because hardware imperfections, whatever, and we can take this into account when we map logical to physical qubits. So if we expand on these qubits, we can say that like in the first qubit, the injection is masked because it doesn't not. I mean, the QVF value is not that high, while the last two generate an error, and like qubits 1 and 2, we can also see that they seem to tolerate faults more as long as this theta shift is less than pi over 2, and then there is no that tolerable effect when we increase both angles to pi, which we see instead in qubits 3 and 4. Today, quantum computers are still reasonably small, okay, like in quotations, there's a debate going on if we are out of the NISC era. I mean, it's debatable. They're not huge, okay, with that we can say. And so it makes sense to try to see how, I mean, what would be the impact of scaling in this context. Here we report the QVF distribution for the circuit considered, with different colors for different widths of the circuit. And for these two algorithms, there's not, it doesn't seem that there is a great impact on like increasing the number of qubits. Instead, if we look at the QFT circuit, we can see that the distribution is skewed to the left. So we have a higher number of acceptable values in general. And we can also see that when we increase the number of qubits, this distribution tends to shrink to the average value. And this means that we are increasing the probability of being unable to confidently select the correct answer. So up to now, we have seen just a single injection. We can also perform a double injection, which means adding another fault on a neighboring qubit of a lower magnitude. And for this, we can take the Bessi-Masirani circuit. We can explode, we can zoom in since it's symmetric with respect to phi, pi. And yeah, we can see in here that the second injection worsens the QVF heat maps. In particular, we don't see the more tolerable effect that we've seen before. We can also plot the delta, so the difference between these two, and we only see like either white or red. So double injection is always worse than a single one. We can also go deep into understanding how this style is computed, for instance. And so we have the gray plane, which is the QVF for the first fault as a reference. And then on top of that, we add the second injection. And we can see that near the origin, we have a lower effect, a higher effect when both tend to pi, and again, a more tolerable effect when both angles tend to pi. And we can also plot like the distribution for this, and as you can see, the double injection is skewed towards the right, so it's basically worse than a single one. So just a brief recap on this logical circuit level injection. The fault propagation is dependent on the algorithm. A higher shift does not directly imply a higher QVF. Different qubits may have different, they may respond differently to injections. And so we should take this into account when we map the logical to physical qubits. Scaling can have an impact, and like double injection is always worse than a single one. And now I just wanted to show you a bit of applications of QuFI. I'm going to talk about quantum circuit cutting, transpiling, and convolutional neural networks. So in the first case, quantum circuit cutting is a novel technique that allows you to split a circuit into smaller subcircuits that can be independently executed, maybe in parallel if you have, like, I don't know, multiple, let's say, small or big enough QPUs. You can work in parallel, and you can recombine their outputs to reconstruct the full circuit output. As an instance, we have this, the QFT circuit. Then we can extract these three subcircuits, execute them the way we want, and then recombining the output. And we have injected faults in each one of these subcircuits, recombining the faulty output with the other subcircuit but without faults, and measuring the impact of that subcircuit on the final output of the general circuit. So taking, for instance, the QFT, we can see that, like, a phase shift of pi on both angles again leads to an ambiguous result in or incorrect result in subcircuit 0 and or 2, while for subcircuit 1 it's like more tolerable. And also we can see that subcircuit 2 is more influenced by theta shifts rather than phi shifts. So up to a certain value of theta, it's sort of safe, let's say. And then we can also reason about, okay, but what if there will be some technique that would not allow the faults to propagate? Okay, I'm not saying we have a solution for this. Okay, I'm just saying, just think that if we were able to protect some circuit, what would be the impact? So how the distribution for the QVF is going to change. So in this way we can learn which subcircuit is the most critical one that we should protect. In here you see again the histogram with the mean, with the distribution. So we have the mean and you have the standard deviation, and we can see that they are pretty much centered in the middle in case of the uncut circuits, and that the various subcircuits have different QVF distributions. For instance, we can see that for QFT, the most critical subcircuit to protect would be subcircuit number 2 in green, because it has the largest mean and the largest standard deviation. So let us try to imagine that we have a way to harden one of these subcircuits. So how would the distribution change? As you can see, and these are the results, this protection may have a significant impact on the overall QVF of the circuit. So starting from like the QFT circuit, we can see that like protecting subcircuit 1 and 2 would greatly reduce the mean to around 0.3, but protecting also subcircuit 0 gives the highest level of protection, bringing the QVF mean value to 0.2. But as we have seen in the previous slide, in the circuit actually, as we've seen in the previous slide, subcircuit 2 is the most critical one to protect. And also, thinking about the circuit, we need to take into account that subcircuit 0 is the largest one, while subcircuit 2 is the smallest one. So I imagine that one should take into account not only the criticality of the subcircuit, but also the size. So depending on the cost they are willing to pay to protect that particular subcircuit. No, sorry, I just clicked the wrong button. Yeah. Okay, so recapping, subcircuits can have a different susceptibility to faults, and when protected, some subcircuit can make the circuit more reliable, and we need to assess what's the cost of protecting these subcircuits in terms of depth and width. The second use case is the one of transpiling, which is the process, again, to translate from the very high level of abstraction from your quantum code throughout the stack to the sequence of gates that you need to apply to the qubits. And this depends on many parameters. It depends on technology, it depends on the gate set for the device, it depends on the connectivity between qubits, and the actual state of the machine. For this analysis, we selected 7 different circuits transpiled over all possible initial mappings, and using all 4 optimization levels within the Qiskit transpiler for a total of more than 4,000 different transpiled circuits, and each of them had a QVF heat map, so we had to average that out in order to have some comparable metric. In here you can see the average QVF value for the 7 circuits for all optimization level transpiler. And again, these are only average values, but already giving some hint of the differences in between them. And in here instead, you can see that for each circuit we have all the possible transpilations with all possible initial mapping layouts, and these transpilations are sorted in ascending order for the QVF average value. So for the different algorithms, the x-axis is just purely a list of the different mappings, and the different algorithms also have many different pools of possible initial configurations, so their length of these lines is different. But then in using this, we can appreciate what's the variability of QVF average values for the different circuits, for the different algorithms, and we have a 14% difference for Grover's algorithm, which is the largest one. And with the, wanting to go more in detail on the behavior for a particular algorithm, we can take the Bersin-Vasirani algorithm on 4 qubits transpiled for IBM Santiago machine. And transpiled of course, on all optimization levels. And we selected Bersin-Vasirani since it's one with the largest number of initial mapping possible. And as you can see, the optimization level 0 is able to achieve generally lower QDF average values, having both the maximum and minimum values lower than the other ones. And also, we can see that optimization level 3 has the largest variability among all of them. We can also compare this with the obtained C0 count and circuit depth, which are the parameters that the Qiskit transpiler tries to optimize for. And it's also interesting to note that the maximum and the minimum circuit are like close. Circuit depth are close for all optimization levels, and optimization level 3 having just a minimum depth of just 2 gates less than optimization level 0 minimum. And regarding C0 count, on optimization level 0, yes, has a maximum count higher than the others, but they are, all the others are basically the same. And again, regarding the counts, all optimization levels report not only the same minimum count, the C0 count, but also like the distribution is pretty much similar between them. In here instead, you can see a direct comparison of the reliability profile for the best and worst transpilation, considering the QDF average value, so lowest and highest. And on the radar graph on the left, you can quickly compare the considered metrics, so QDF average, C0 count, and circuit depth, normalized from 0 to 1 on the total number of gates. And while the heat map for the best transpilation shows a significant vulnerability only when phi tends to 0 and theta tends to pi injection, the heat map for the worst transpilation has definitely a wider range of angles that have a detrimental impact on the output. And we can also like see this from the figure on the right, which is the delta of the two heat maps, since it's composed only by white and blue colors. The best is always like better than the worst in all 4 pairs of angles injected. Recapping this, the Qiskit transpiler working at optimization level 3, yes, it produces shallower circuits, but they are more prone to faults, so up to 14%. And depending on the application, we can add this the QVF as a metric in the trade-off, between the transpiling approaches. The last use case I wanted to describe, to report to you, is the one of convolutional neural networks, which are the quantum equivalent of convolutional neural networks. And they have applications to image classification, delivering interesting speed up, both in terms of convergence and inference times with respect to the classical counterpart, and also maintaining similar classification accuracy. And in this study, we analyzed three QNN models based on the hardware efficient ansatz, which uses amplitude embedding. And so each of these models have different network depth. We use two datasets, NIST digits and fashion, and we track the error propagation through qubits, channels, and subgrids, identifying the faults that are more likely to cause a misclassification. This is the generic architecture of a hybrid QNN with a detail of the Q layer. This model was found in literature. It was already quite used, so we decided to analyze this one. In this model, the input image is divided into 2x2 subgrids, and then we have this 4-qubit quantum circuit performing both the convolution, 2x2 convolution, and the pooling operator on each subgrid. So this is the general architecture, and we studied the three hybrid networks. This is the combined view of these three models. We have model A composed only of only a quantum layer, a Q layer, is convolution in blue, directly connected to the flattened layer. And then we have model B with convolution and the green traditional convolution layer. And then model C, which has all the elements in the figure. This is the ansatz circuit that implements the convolution. These the values that that parameterize the rotation gates are randomly generated and kept constant for all the experiments, and these are the values used. The QVF heat maps for this circuit suggest that the theta shifts are critical, while the shifts on phi are not. And this is due to the use of amplitude embedding. So since we are encoding the state on the meridian of the Bloch sphere, it makes sense that shifting along this dimension has a greater impact. So, but then we are willing to understand if they are if the network is classifying correctly. So we need to introduce a bit of nomenclature. We have masked fault if the fault did not corrupt the softmax vector output. of the network. We have a tolerable fault if it modified the output vector but did not alter the output predicted class, and misclassified if it modified the output vector and did alter the output predicted class. So in here, for instance, you see that the fault-free execution in green and the fault execution in red on the right side, and sorry, on the left side, we can see that the confidence for class number 2 is pumped up, but still we are able to confidently select the class 0, which is the correct one. So in this case, it's a tolerable fault. Instead, on the right, we see that the fault changes dramatically the output, and increasing the probability of selecting class number 4 and also 5. So like the correct class, which is 6, is the third most probable to be selected. We can also check the misclassification probability dependence on the data that we are analyzing. In here you see the heat maps showing the misclassification probability for faults injecting in each subgrid, so in the coordinates of the image, and for both the datasets. And as you can see, the datasets have a very different reliability dependence on the correlated subgrid. Like on the left, for instance, you can see that some subgrids are very likely to generate misclassification, while others are a very, very low probability of impacting the output. For instance, like row number 4, column 7 has a misclassification ratio of 10.3%, while a fault in row 1, column 5 has a 0.8 probability to induce a misclassification. So pretty diverse. And while instead for the fashion dataset on the right, the heat map is pretty much homogeneous, suggesting that the probability of incorrectly labeling an image on this dataset is not significantly dependent on the corrupted subgrid. And also to understand if the QNN design impacts the fault propagation, we inject in a single random subgrid of the Q layer in model A, B, and C, to test how much the downstream classical layers have an impact on the propagation of the fault in the quantum part. And these figures plot the misclassification ratio with respect to the fault angle, amplitude theta, again on different models, considering a single failed subgrid on the digit dataset. And we only report the theta because on phi we have seen that it doesn't impact that much. So starting from model A, we can see a direct correlation between the angle, theta, and the misclassification ratio at the output. We have a ratio of 3.18% at pi over 2 and 6.43 at theta equal to pi. And given also the relatively shallow architecture of model A, the classical part cannot compensate for the fault, and also no masked event was recorded. For what concerns model B, we still have this correlation with theta, and again in this case we don't see any masked event. For model C, instead, on average, we see stable distribution of masked events with probability around 26%, and this can be explained by the fact that increasing the number of filters in the classical part can disperse the effects of a portion of the faults introduced in the quantum part, so they get cancelled out. And in general, in a quantum workload, we cannot rule out the possibility to experience multiple radiation-induced corruptions across the whole execution, especially in iterative approaches such as QNNs. And we can expect to also have a single particle deposited charge corrupting multiple logical qubits, or possibly like several Q-layer circuits. And as a final analysis, we have injected into two separate random subgrids at the same time, and so we have two injections in here on the right, and the correlation again with the amplitude, between the amplitude and the misclassification ratio is evident. At theta equal to pi over 2, we have a double effect than a single grid corruption at 6.24%, and at pi it tops up at theta equal pi, it tops up at 9%. And also, of course, we conducted tests for the other models showing a steady increase of the misclassification ratio, and also for model C, we have a reduction of the masked faults. Recapping this last application, the corruption of the Q layer significantly impacts the QNN operation and classification performance. Theta shifts in this case with amplitude embedding is very likely to propagate in the QNN, and up to 10% of injection induce misclassification. And this misclassification probability depends on the magnitude of the shift injected, the subgrid that is corrupted, the data set that's being used, and the number of classical layers that follows the corrupted quantum layer. So wrapping up this presentation, quantum computing can dramatically benefit scientific computing, but we need to handle the integration within HPC system. And in this context, noise is a great issue, And QuFI can help at many different levels for building resiliency in these hybrid systems. I thank you very much for again for the invitation and for being here to listen to me. In here are the references, and I also wanted to take a minute or less to invite everybody watching to please submit to the special issue on frontiers in computer science. So if you're working on compilation, on verification of quantum circuits, on hybrid algorithms, on post-quantum cryptography, you are encouraged to do so. In here you have the link. And of course, I'm not alone in this endeavor. We have Kate Smith at Northwestern University, Shuai Shu at Case Western Reserve, Ed Yunis at Berkeley Lab, Fong Kao at University of Illinois, Urbana-Champaign, and Betis Baheri at Kent State University. That was all I had to say. Thanks again.
Great, thank you. Thanks, Edu, for a great presentation. And now it's time for questions. So I can already see several questions on our chat. So the first question is from Louis Rifkin. Louis, would you like to unmute yourself and ask? Or I can just read it as well. So the question is, does more work need to be done on the materials that are used to construct quantum computers to avoid the problems encountered when dealing with the side effects in the quantum realm? For example,
Yes.
particle diffusion.
Yes. I mean, there are many groups throughout the globe are working on improving whatever possible parameter you can think of at the hardware level, really. From the purity of materials on how you build the junctions, how do you etch the materials on the substrate, how do you build the layers for transmon qubits. There's plenty of people in the US, plenty of people in Europe working on this.
Okay.
Okay,
Good.
thanks.
Thanks. There's another question from Mariam. How do you see quantum computing impacting the field of radiology, particularly in terms of image processing and analysis? And there is a follow-up question. What are the current limitations or challenges in integrating AI with quantum computing in the context of healthcare applications?
I'm not an expert in healthcare, but I have seen that I mean, as you can see, like in this case, there are applications for image processing, and I think I think we're gonna see many more developments in this domain, and I think I hope actually that QC is going to be applied, to medical imaging to hopefully improve the accuracy for I don't know, like tumor diagnose and so on. I think it's going to be applied a lot. And regarding how to put there is some effort in trying to build a bridge between quantum and AI. The group, for instance, of Alan Aspurgudzik at the University of Toronto, where a friend of mine, Mohammad Gazibakiri, is working at. They have a recent paper on specifically on this, so I encourage you to read it, and or you can reach out to me, and I will, I mean, give you the link and
Mm-hmm.
whatever.
All right, good. Thanks.
Thank you.
Yeah, so actually, there's also a follow-up question from Mariam about resources or training opportunities that you would recommend for researchers interested in exploring the intersection of AI and quantum computing. So there's already one good
Yeah.
recommendation on our chat, but if you have some other links, so other resources.
I don't remember, I don't know what I, let me see the chat.
Mhm.
What's the what are they suggesting?
Yeah, so I suggested, so there was a conference on quantum machine learning that the Quantum
Ah,
AI
okay.
Foundation organize once
Yes.
per year. So this year
Oh,
was the
yes, yes,
fourth
yes,
edition
yes.
already, and there are video recordings available.
Yes, in on YouTube there is an excellent series by organized by Peter Vitek,
Mhm.
one was one of the like many I mean one of the few actually very important people in quantum machine learning that had an accident when he was like climbing uh, Everest, I believe.
Mhm.
So he's not, unfortunately, he's not pushing anymore for the field of quantum. And I mean, the humanity regrets this, but you know, life happens. And so I do encourage you to look for that. It's like uh, I think quantum machine learning MOOC, so MOOC, so like those
Yes,
online course.
yeah, I just put
Uh,
the link
if you have okay,
this
oh,
this link.
perfect. Yes, yes, okay. Thank you,
Mhm.
Pam. Thank you.
Thanks. Thank you. All right, we have some further questions, this time from Harish. Should we have to learn the operations, optimizations on qubits to learn AI models on quantum computer in the future? Or it would be the same like GPU, TPU usage going forward? And there was another question. If we have to
What
dwell, yes, yes. So let's first
I
try
don't
to ask this
understand
one.
this.
Yes.
Oh wait, I
So
don't understand the.
Harish, maybe you can also unmute yourself and clarify.
Sure. Thanks, Pavel. Hi, Edo. Thanks for the
Hi.
session. It was a simple question like, should like at the present moment on GPUs or on TPUs, we don't go at transistor level or at the chip level, what's happening
Mm-hmm.
on the numbers, how the processing are happening. But coming to the quantum
Yes.
world, which I'm very new into, looking at the slides and knowing the operators or the operations happening or the effects or the errors at the present moment, should we have to really
Yes.
learn everything, all of these points for AI models to work in the future?
I mean, hopefully not. Meaning that like this effort that we are into, it's actually, uh, we have a huge like software stack that enables you to write some program that's some uh, AI, some AI algorithm that's executed on a GPU, and everything like it's abstracted, so you can, the wrappers written in such a way that you see just, APIs to work on with this stuff. You don't actually see like at transistor level what happens. So I believe that in the future you will not need to know such things, but you need to keep in mind that in like the quantum field, quantum computing field at the moment is like being in the 50s for transistors. So we are like still developing the technology. But then since we have, I mean, it's it's going the other way around. Like before, we had before it came the transistor, and then we built stuff on top of that. In here, at the moment, is the other way around, because we have quantum algorithms, but we don't have the hardware to execute stuff. And so now we need to. There is a load of software that we still need to write, that we still need to develop, in order for you to abstract whatever is down and then just use these devices the way we use GPUs and TPUs right now. So there is plenty of stuff to be done, and I encourage you to get involved.
Yes, I
Many
wanted
people.
to. The follow-up question is on the same thing. I wanted to involve, and if so, what is a good source of starting and understanding the basics, like respecting the fundamentals?
I think the IBM Qiskit series by John Waters is excellent.
Yeah.
I mean, that's the first thing I say to everybody. That's just nothing bad can be said about that.
Oh,
It's just what it is.
thank you. Thanks, Isma.
Thank you for the questions.
Thanks, Victor. Thanks for the presentation. It was a great day.
Great. Thank you.
Thank you.
Thanks, Harish. Okay, I can see that there was maybe one more question from Louis Rifkin. Louis, do you still have a question that you would like to ask?
No, I'm good, thanks.
Oh, okay. All right.
Okay.
Yeah, so there was a question on YouTube. So thanks, Helen, for this. Have you explored the QuFI approach to other architectures such as optical neutral atoms or even quantum analog simulators? So basically,
Not
other than
right now. Yes.
superconducting.
Yeah, at the moment, no, but yeah, we could do that. It's a matter of trying to understand what are the. I mean, it would be very nice to tweak because it's very very general at the moment. You can tune it for whatever physical device. So whatever technology, actually, if you're willing to do this, please reach out and we can talk.
Okay, good. Thank you. All right. Do we have more questions? Because I think that we've already asked all the questions that.
Sorry to cut you in, but may I know so the name again from the IBM, Professor?
John Watros. But if you look for IBM Qiskit lecture series Quantum Information Science, it's like 10 lesson course, and it's
got it. I found it. Thank you.
Okay. You're very welcome.
All right, good. Thanks. All right. Do we have more questions, Edo? Let's wait for a while because currently I don't see more questions on our chat.
Okay.
Helen, maybe you can check the YouTube once again.
I don't see more questions on YouTube right now.
Okay, good. All right, last chance then.
I mean, people, you can also reach out to me.
Yes, by email.
In here. Okay, and in here you have the there is the link to my very fancy website, which is basically a list of stuff, and then this is my email, so ejusto@ieee.org.
Okay, good.
And that's it.
Thanks for this. All right, we don't see more questions now. So, Edu, thanks once again first of all for the great presentation and also for answering all the questions. We'd also like to thank our participants for attendance and asking the questions. So there was an interesting discussion as well.
Yes.
Okay, and we hope to see you next time on our next meetups.
Thank you. Thank you very much for the invitation. Have a great day, everybody.
Have a great day. Thank you. Bye bye.
Nice. Bye bye.